Good afternoon, everyone. We're going to get started here in just a minute or two, give people some time to sign on, and we'll get going. For those of you that are just signing on, we're just giving folks a couple minutes to get logged in, and then we'll get started probably around 5 after. We'll get started here in just a minute. We're just waiting on everybody to get signed in. Okay, hello and good afternoon, everyone. I want to welcome you and thank you for joining us for today's webinar on feeder automation and distributed energy resources. A couple of quick housekeeping items before we get started. All of you attendees are on mute, so if you have any questions, please post over in the questions panel. We'll do our best to answer your questions, but if we can't get to yours for some reason, we will follow up with you in an email. At the end of this webinar, there's going to be a 3-question survey. Please take a moment to complete that, and if you have to sign off early, we will also email that to you. So with that out of the way, let's dive in. The utility grid is changing faster than it has in the past, resulting in what can be summed up by 4 Ds: decentralized, digitalized, decarbonized, and democratized. With this paradigm shift, grid operations must adjust to address these new challenges. Grids will soon have to deal with non-dispatchable intermittent generation that is significantly influencing the foreseeability of loads. Grid control must be able to respond dynamically to localized conditions, and grid operation must be able to extend real-time visibility to sections of the network that are seldom monitored, let alone automated today. Today, we'll discuss how to leverage IT and OT technology that is already available and proven in utilities and other industries to design cost-effective solutions to distribute automation and to include DER as part of the dynamic operation of the network. Your presenters for today's call are Lee, John, Giovanni, all from ACS, along with over 100 other utility professionals. So with that, thanks again for joining us, and I'll turn it over to Lee.
All right, thank you, Delana, and welcome everyone. I want to first make sure I've got control here. And it doesn't look like I do yet. So Delana, would you go ahead and forward the slide?
Yep, sure will. You want one more?
Yep, so I'm seeing the initial screen.
All right. You should have control, Lee.
Is that me? Okay, great. Well, thank you again. Sorry for the trouble. So Delana has introduced these 4 Ds, but what is really influencing this paradigm shift? So our customer, they're no longer just a ratepayer. They're more informed. They want expert utility engagement. They want and expect utility engagement. And there's an entire generation that is a digital native. So there's a commercial, industrial, and everyday consumer sentiment shift toward decarbonization. We now seem to be calling this movement the prosumer. A customer who wants to generate electricity and participate in the market. Storms are frequent and devastating, putting additional pressure on utilities to not just harden the system, but potentially distribute control more locally. Communication infrastructure is better. Computing is smaller, faster, and more affordable. Digital transformation is happening all across industries. We don't have a choice on whether we digitally transform. The choice is how well we do it. So it is evident, particularly regarding investor-owned utilities in the U.S., that our regulatory model has not kept up with the evolving needs of our industry, and that each state has their own unique situation based on many influencing factors. The pace is faster in some states than in others. However, this doesn't mean that some of you aren't already experiencing the impact solar and battery storage is having on the distribution grids that you're charged with maintaining. So today, we want to share what we've learned as a utility grid control systems provider, working to take on some of the challenges our customers spanning the globe have been facing over the last several years. Our approach has been organic, our findings built on real-world applications. We'll discuss auto restoration and how the solution we developed for Georgia Power in 2011 led us to an early understanding of scalable, interoperable, and important for today's discussion, distributed architecture. Using these learnings to approach a more recent project with San Diego Gas and Electric, we discovered this distributed architecture also performs well when applied to voltage stability and system reconfiguration on a collection of feeders with a high penetration of DER. In closing, we'll discuss a forward-thinking project that we have launched in Australia along with Monash University on the application of IIoT specific to utilities. So some of the following information It's from a 2015 Transmission and Distribution World article that was co-written with Georgia Power. We'll of course send you the link to this article and a few more links and information in a following email after the webinar. So Georgia Power is an investor-owned utility serving over 2 million customers. The most densely populated portion of Georgia Power's service territory lies in the middle of the largest urban forest in the U.S. The entire state's above average forestation includes high portions of relatively weaker pines, which increases the destructiveness of the storms, particularly the damage to overhead lines from falling trees and limbs. So in 2010, Georgia Power set out to improve reliability and increase the distribution automation capability of the distribution network, systematically starting with their most impacted portions of the grid. The key goals of the project were to overcome the uncertainty of what might happen in an outage condition by deploying the best self-restoring technology possible. In short, identify and isolate faulted line segments and restore service to customers on unfaulted line segments, fault location, isolation, and service restoration. So we'll shorten this going forward for the rest of the webinar and call this FLISR. So the solution requirements: the system must be safe to operate with system overrides. It must ensure system stability by enabling manual restoration. The system must gather fault data from devices and send status directly to an OMS or DMS. It must deliver enhanced reporting to include automated calculations of CMIs, and that would be customer minutes interrupted. And importantly as well, it must work with existing infrastructure. So forms of FLISR date back in the late 90s to the late 90s. And the applications really branched out into somewhat divergent approaches to automation. One being the distributed, scripted, logic, rule-based type system, or a centralized model-based approach. So each, even 20 years later, seem to still come with their own challenges. The Georgia Power pursued a solution developed by Advanced Control Systems that would provide the benefits of both, and the project was dubbed Centralized Restoration Gateway. The enabling ACS technology is what we call Centrix. So the benefits of this approach gave Georgia Power a dynamic local model. No GIS data is needed for this, and it's based on a pre-existing feeder template. It integrates with existing and future equipment, scales incrementally, and can be updated and configured remotely. So the system essentially isolates and restores within 1 to 2 minutes, instead of the, at the time, 15 minutes or longer it might take to determine the right switch plan using an OMS and manually switching from SCADA, for example. An even bigger impact was it in areas without any automation at all. Therefore, they'd be reliant on a distribution line crew to be deployed, only when it's safe to do so. With automation, those CMIs were improved dramatically. So an additional benefit is that the automated system frees up operators for higher value tasks during emergencies, while still giving them the option to override and control should they need to. So the first system went online in December of 2011, but the rollout really began in 2013, extending to about 370 feeders by the end of 2015. So some notable results. In 2017, over 52 million CMIs were avoided, contributing to 21 SAIDI minutes. And this was during Hurricane Irma. The next year, 2018, for the total year, it's 82 million CMIs, contributing 32 SAIDI minutes. The system continues to expand as an extremely cost-effective solution and now serves 790 circuits, improving the reliability for 1.3 million customers to date. Now, while we're very happy with the success and the expansion of this application, the key findings for our message today is that these controllers or servers sit architecturally and physically outside of the centralized DMS and work as a coordinated but autonomous system. The additional value this brings to a network is resiliency and reliability, as these systems can act as independent nodes operating within selected portions of the grid. They can also more efficiently process large amounts of data more locally. The logic, the rules, the system modules are located in multiple dedicated servers. They collect data, they make control decisions, and they issue commands to SCADA. So this leads us to our next example. In 2016, we began work with San Diego Gas and Electric as a part of the California EPIC project, where we've expanded this application to include additional functionality that I'll let John Groder share with us now.
All right, thank you, Lee. So Lee did a great job of giving us an idea of how this decentralized solution will work. So what we did that next was take some of the concepts that we learned with Georgia Power, and we wanted to add more distribution assets, and primarily we wanted to add larger utility scale DER to this concept. So with that, we added into these models, these distributed models solutions, we added large scale PV as well as utility controlled distribution scaled battery storage units. And what we wanted to do, a lot of times utilities add these as very singular use cases, as either maybe offsetting peak load, but what we wanted to do was actually bring these assets and how can we utilize these in distribution distribution operation to help mitigate some of the potential problems that they may lead to. So with that, as Lee mentioned, this was part of a California EPIC project, and what EPIC stands for is Electric Program Investment Charge. And these are programs that are financed by the California Energy Commission, that they invest in scientific and technological research to accelerate the transformation of the electricity sector to meet the state's energy and climate goals. These projects provide benefits to the California IOU customers of Pacific Gas and Electric, San Diego Gas and Electric, and Southern Cal Edison. This particular project was called EPIC 1 Project 3, and as Lee stated, it was started in 2016. It was a joint collaboration between SDG&E, ACS, and Quanta Technology. And the topic of this particular project was specifically distributed control for smart grids. So some of the project objectives. First, they wanted to compare two traditional schools of thought, centralized versus distributed control. So as they hypothesize, as higher penetration of smart field devices come onto our systems, it's logical to have control closer to those intelligent devices, thus leading to a more distributed control architecture. Also, the distributed control architecture should reduce latency to be able to react to events much quicker than a centralized system. Also, by nature, distributed control approach should be more reliable compared to that of a centralized. So with this, they wanted to simulate all these various use cases. So they needed to build a test bed to simulate all these multiple use cases. But they wanted to model an actual portion of their system to make this most realistic to their application. So they built the test bed using both hardware and software in the loop, and they built it at their integrated test facility. And again, they wanted to pick a part of their system that had reliability concerns, high penetration of solar, presence of sensitive loads, and customers with premium power quality requirements. By selecting this particular application, they were able to get more use out of this proof of concept. So integrating these utility scale DER into grid operation, we're going to talk about two of the different use cases that came out of this report. One was DER integration and management and using what they called automated resource control. And the use case two, operation and control, and also doing a synchronized load transfer that we'll talk in detail. And then obviously they wanted to analyze the findings at the conclusion of this and produce a report that would provide useful takeaways, not just for San Diego, but also for the industry as a whole as we move towards a new way of grid operation. So use case number one. So this shows a simplified one-line diagram of the portion of the system that they wanted to simulate and do the various test cases against and look at various scenarios. So as you can see, this is composed of two different substations with two main feeders coming off of each substation. One, the Creelman substation, and the other one, the Santa Isabel substation. And they have both existing devices, so they modeled all their existing devices, including load tap changer controls on each transformer, all the different reclosing and sectionalizing devices, as well as capacitors and voltage regulators, as shown here in the blue circles, as well as the added larger scale DER. So on the Creelman feeder, we have a 2 megawatt PV array, as well as a 1 megawatt PV array further down line. Also on Creelman back at the substation, a larger utility scale battery storage, 2 megawatt battery storage. Coming off the San Isabel substation, the main feeder, we have both a 2 megawatt PV array, as well as also an additional of a large scale battery storage unit downline of one of the feeders coming off the San Isabel. So the first application that they wanted to utilize automatic resource control was doing a volt-var optimization, or VVO scheme. Now, VVO has been around the industry for quite some time, and it's been utilized to reduce system losses and make the feeder more efficient. However, another reason for coordinating all these devices is to allow for a more optimal operation system, not only to reduce losses, but also flatten the voltage profile. And why is it advantageous to flatten the voltage profile? Well, when you do that, instead of having a large voltage drop from the front of the feeder down to end of line, the flatter you can make that voltage profile, the more elasticity, the more flexibility that feeder has. And that's important. As we are adding more intermittent generation onto our system, voltage will become far more dynamic, and feeders and distribution lines will need that type of elasticity. So flattening that voltage profile is critical to adding more DER onto the system. So what they wanted to do is first compare how they're currently running these various devices, which is just from a local control based on conditions that those controls are seeing. So the voltages and currents that the voltage regulators, capacitors at the point of the system that they're at, they're just operating autonomously. They wanted to compare that to the ACS model-based distributed volt-var approach. And then they wanted to compare both of them and simulate one of these large PV tripping offline and see how each different method would react to that certain scenario. So with that, we have two different charts here, and the way you can read them is time comes along the x-axis, and we are modeling 3 different voltages on various points along each feeder, or along the feeder. We have the 1 voltage point at the head of the feeder, 1 towards midline, and 1 towards the end of the line feeder. And as the time goes along, we trip right around 100 seconds, as shown on the left graph, is right when the large PV trips offline. So some things that we can take from this. First, the chart on the left shows the devices working autonomously. These are just the voltage and capacitor control devices working autonomously based on the conditions that they're seeing on their part of the feeder. So some takeaways we can take from this is, first of all, in the steady state condition, prior to anything happening, you can see that there's still a pretty large voltage gradient between both the head and end of line. It's not a very flat voltage profile. So again, as voltage becomes more dynamic, as more intermittent generation comes online, you have less flexibility along that feeder. Next thing that you can take away from the first case scenario is when the PV trips offline, there is a 60 seconds before the midline and end of line voltages start to recover. Now that's direct correlation to how those controls are actually set up. So clearly there is a large time delay before those controls start reacting. And then the third takeaway you can take from devices working autonomously by themselves is, even when they return to a steady state, you can see that there's still a tremendous voltage gap and a large delta voltage between the head and midline voltages and the end of line. Also, the red indicates various violations, voltage violations. The lighter red shows an area where temporary voltage violations can occur, and the darker red is voltage levels that should not be penetrated. So then compare that to using the distributed VVO approach from the ACS system. And first we can see in the steady state condition, the voltages are much closer, thus having a much tighter and flatter voltage profile. But then also when that large PV trips offline, you can see that the voltages react far quicker than in the previous example. And then finally, you can see that the voltages are flattened and you are very tightly integrated and this is using a model as a whole as opposed to just seeing certain points on the system. By using the model of the entire feeder, you're able to optimize it far better than just the controls working autonomously. Also, this VVO scheme utilized the reactive power, the smart inverter capability of the DER assets to also use the DER as part of the volt-var optimization scheme. So that helps kind of fine tune beyond just the traditional devices of regulators, LTCs, and capacitors. Those inverter-based or those inverters also contribute to being able to flatten this voltage profile. So with that, moving on to use case number 2, operation and control and synchronized load transfer. The first thing we'll look at is utilizing forecasting data. So this is both weather and load data to run what we call a feeder injection test to attempt to identify any system violations prior to occurring. So what we're doing is using a rolling forecast data to continuously run future load flow analysis. And if after running that analysis, if any violation is determined that can be mitigated, that cannot be mitigated from automatic resource control, as shown in use case 1, attempt to identify a new system reconfiguration, perhaps create new switching plans to maybe alleviate certain voltage or certain system violations, whether that's voltage or reverse power or any other violations or constraints that may hinder the distribution system. So, however, there are times that system violation issues may not be able to be mitigated from either using automatic resource control or from forecasting analysis. As we all know, events can happen on the distribution system that will cause us to think in a more of a real-time fashion. So that leads us to a real-time system configuration or real-time system reconfiguration. So what we want to show here, that we're showing the same example here. Coming off the Creelman feeder, we have a load coming down line, and what we wanted to model was a loss of a large load. How would this react? So as you can imagine, if you lose a large load, and maybe we're in a middle of the day, noon, 1 o'clock, we're going to have a maximum amount of PV injection from these downline PV arrays. That loss of large load, when this normally open tie, will most likely cause an overinjection and possibly a reverse power even up onto the subtransmission level, which may not be desirable. So instead of just simply curtailing those large PVs, what can we do, since we're looking at this system as a full model? Can we use assets on an adjacent feeder to possibly revert some of that power injection and not just have to rely on curtailment? So with that, the model, so we show over injection. The model looks and it sees that we have this large battery storage device and it has available storage capacity. So with that, what the system can do is then do what we call a synchronized load transfer across this normally open tie. So you would need to make sure that you'd have to have a sync check in place, and you would want to be monitoring the voltages and controlling the voltages across that normally open tie before you close in and create that loop feed. But once you can do that and do a real-time system reconfiguration, you can now divert that power injection and still utilize it without curtailing it and utilize that available storage capacity. So coming to some of the key findings that came about from this project was, first of all, distribution architecture showed promising benefits compared to centralized. So data acquisition times are reduced since there are less downstream devices that need to be serviced, so response times are faster than the centralized equivalent. it was actually estimated that the distributed approach could reduce latency by over 50% compared to a centralized approach. Also, utilization of existing grid assets to work holistically with added DER. So they successfully showed how this approach can incorporate existing grid assets like regulators, reclosers, capacitors, with the addition in a holistic fashion to maximize feeder efficiency. Also, integrating larger scale DER to assist with grid reliability. So this distribution automation demonstrated not only can DER challenges be mitigated, but it also showed how you can actually use the DER capabilities to improve grid reliability. And then finally, use case 2 covered in detail how you can employ forecasting data to predict and mitigate potential grid violations, as well as doing a system reconfiguration to address system constraint violations. So as we move along the journey of the evolution of a distributed control system approach, we've shown how we can we've shown by Georgia Power how we can integrate smart devices, and then with Epic how we can bring in those utility scale DER assets. The next step in this journey is to show how a distributed control approach, how you can scale it when adding a tremendous amounts of more devices closer to the grid edge. So that includes integration of behind the meter DERs, as well as flexible load control with a more real-time demand response. This is all part of democratization of the grid, so allowing for more customers to participate in grid services, as Lee alluded to at the beginning. So utilization of a grid edge computing technology and IIoT capability of handling tremendous amounts of data, which leads us to another D, digitalization, to make intelligent decisions in near real-time fashion and closest to the edge devices allow this to happen. So Giovanni will now discuss how this technology is being implemented in a very exciting project that is underway in Australia.
Thank you very much, John, and welcome to all. So it's a great pleasure. I think I should now have control. So it's a great pleasure to be here, and hopefully we have so far explained the topics that our audience has found interesting. So regarding the last real world application of technology and putting together 2 cases that we just have seen, we show you the experience in Australia. So why Australia? Well, Australia has the world's highest penetration of small-scale solar, as you can see from the graph in the slide, where each state is indicated here in the graphs, and you see the growth of the penetration during the years. So in terms of installed power, it's almost 1/7 of the total capacity of the energy market in Australia's East Coast. So, and it is undispatchable. In the USA, to give an example, the highest penetration is in Hawaii, and it's just 14%. So a value that Australia had only 4 years ago, if you can see from the graphs. So in only 4 years, Australia has changed the way power flows across the grid. Some states, as you can see, have almost 30% of residential customers with solar panels on their roof. Australia is experiencing how the grid can reach its limits when it comes to integration of DR without any substantial infrastructure investment, because it's happening very fast. So not the outages of frequency, probably the opposite, but utilities have in the last few years embraced a non-network solution to manage the high DR penetration in their grids. Solutions that can integrate behind the meter DR in the network operation are looked upon with great interest, because using the available resources is faster and more effective than new capital investments. Startups, for example, and established business are growingly providing solutions for utilities to integrate DR in their control system. However, passing from a few tens of control points of a pilot to the hundreds of thousands of real DR points is proving rather challenging. So in this scenario, we must see the project of the Smart Energy City at Monash Clayton campus that MinSight launched in 2017. The Monash Smart Energy City project is pushing the boundaries of technology to experiment with the industry what the benefits and challenges of DR-intensive grid-connected network can bring to customers and to the outer network to the energy markets. So you see here the Clayton campus, which, by the way, is so large that it has its own postcode. It's near Melbourne in Victoria. Monash University has challenged the traditional way of operating a grid. Basically, they decided to run their network with the coordination of variable loads, renewable energy generation, and Australia's largest behind-the-meter energy storage system. From the initial idea, the Smart Energy City at Clayton campus was meant to show to the power industry that IDR penetration and load control can be used to guarantee the same power quality constraints the utilities must comply with. So the initial scale and the scalability is one of the driving parameters in every technological choice that we did in the project. Monash, by the way, is also leveraging the flexibility allowed by the absence of a regulation that applies to their grid. And with the collaboration of the Faculty of Law, is reporting to the regulator the opportunities the changes in the regulation may bring to the whole industry. The coordination of several loads, such as 20 buildings and an EV charging infrastructure, of solar PV installation and 1 megawatt-hour of energy storage, is performed through the hybrid, that means centralized and distributed platform, one-side AGM. Each load, source, or controllable grid device is connected to an intelligent IIoT processing node, pretty much like our colleague John was indicating before. So this node continuously processes data to analyze local power quality issues and to perform control actions to prevent the escalation of any negative effect. There's a centralized platform that executes the coordination of more nodes, dispatching control commands. The nodes can also trigger events on their own, that, for example, asking for requesting a centralized platform to do a coordinated action. Typically, SCADA and DMS would monitor only feeders and at substation level and not monitor many of the assets connected to them. So to extend the reach of traditional systems and to make this solution scalable, the use of IoT becomes essential. And that's why we basically chose this configuration. Now, from a market perspective, Monash registered a grid operator. You can see over there the connection point with the network. So from a market perspective, Monash registered a grid operator to sell power and service to the outer market. Internally, each building is considered a customer. Each customer can expose its energy flexibility and load of generation to the internal Monash operator market by using the smart energy management platform that Insight is developing. The energy price presented internally to the customers is indexed to the market price, and the cost of energy are then accounted for to each customer accordingly. The Monash operator can control the peak load and avoid heavy demand charges for the campus. And when required, the Monash operator can provide network services to the utilities, for example, when internal consumption is lowest during weekends and holiday periods. As a side note, let me please also say that the project has received the approval of the Australian government through the Australian Renewable Energy Agency, which, after a very deep audit of the scope and its feasibility, has liberated almost $3 million Australian dollars to partially cover the $7.5 million of the total cost. Let's go into more details about what we have here in Monash campus. So the hybrid, centralized and distributed platform is composed by three-layered solution. They maintain separated the basic functions. These functions are commercial dispatching, operational monitoring and global control, and physical connection to the grid for local, real-time, and near real-time interactions. It is very important the independence of these three components. Actually, it's crucial for the flexibility and scalability of the solution. So this allows us to adapt to different markets and different sides of implementation. And it's a great value because this flexibility allows any utility to perform a gradual uptake of the DR integration in their operation. So from top down in the platform on the left side, the smart energy management component is the tool through which each DR and flexible load can be registered in the market, and also is the tool through which customers expose their flexibility to prices and time of the day. The focus is always the customer, and so the smart energy management component must be able to integrate with third-party applications, such as those, for example, that are already provided by manufacturers of inverters or by manufacturers of thermostats. The openness is a critical point for this entire solution. This component is also the one that aggregates all flexibility in terms of available generation or demand reduction, or allows Monash to operate and offer energy to the outer market. The other component, so the active grid management, is the same component that John referred to in his presentation. So maintains power quality and eventually overrides market dispatch if required for grid constraints. It is also the means of communication with the outer grid for the integration of DR in the grid operation. It can, in fact, receive dispatching orders directly from the network substation or the utility SCADA. So lastly, the last layer, the DR integration. So this is the IIoT layer. It's the connection with the physical world, with the DR inverters, with the smart field devices, with the building automation systems. All are interfaces through the other two components. This layer is where the intelligent nodes perform data analysis and send set points to grid assets for a very much localized control, such as, for example, flattening of voltage profile. Each node can run application through containers. It is therefore open to third-party application, should there be the interest, for example, to run specific algorithm to analyze the performance of a transformer or to forecast 10 minutes ahead the generation of a PV site. One of the key software components of the intelligent nodes is the protocol manager, used to configure several communication protocols with the different assets to be connected. Openness is again important, and the data processing module is therefore a pure software component that can be deployed on any Intel-based gateway. So leaving this option open for the utilities. We're not looking to lock in any gateway manufacturer, the utilities. The project has recently completed the integration of all the grid connected assets for monitoring and manual dispatch, whereas the active grid management is due early next year, and the market platform that will also use a blockchain technology to settle payments is due in October 2020. Nevertheless, Monash has already issued their first studies of the regulation and proposed them to the Australian Energy Market Regulator. Before I finish, let me also mention that Smart Energy City and Monash is a project within a much larger initiative within Monash University. Monash University has committed to reduce their emission to net zero by 2030, and that is transforming totally the way they look at energy and the way they think about energy, the way they use energy. The objective and the steps taken since 2015, when the net zero started, have gained international attention in February this year, when Monash was awarded by the United Nations the prestigious Momentous of Change Award in Poland. And I'm trying to, wrapping up the presentation, I would like to recall the three applications we have seen. A decentralized and digitized control solution that extend the reach of any DMS to automate feeders, and has been successfully and extensively deployed at Georgia Power. We have then seen that a localized control is indeed more effective than a centralized one when it comes to integrate DR in feeder automation, and this helps greatly in decarbonizing the grid. Lastly, we have included the customer who can provide services to the network and be correctly compensated for it. Talking about the democratizing the network, for example. Now, we now start going through the questions that have come from the audience during the webinar. And
and so while they're looking at the questions, this is Lee Yance again. For those of you on the call who may not know, Advanced Control Systems is headquartered near Atlanta, Georgia. It's been providing utility solutions to utilities for well over 40 years. So we went to bed in August of 2018 as a grid operations tech company, and we woke up in September as a part of Indra. Indra is a worldwide IT leader. Together, we are an insight. So we are meeting utilities worldwide at the crossroads where grid operations must, more so now than ever, integrate with IT infrastructure and systems. So thanks everybody for joining again. And John, what questions do we have?
Yeah, so we've got several coming in, so please continue to submit questions if you have it. We wanted to purposely leave some time for some good interaction. The first question that came in is actually one that, yeah, we probably should have done a little better explaining. Sometimes we assume too much, and we certainly live in the world of acronyms, but somebody asked, please explain the meaning of DER. So when we say DER, we're referring to distributed energy resources. And the way I look at DER is any sort of generation that comes on to, that is directly connected to the distribution grid, as well as any sort of load flexibility where you actually have control of any load. So that includes demand response, EVs where you may have flexible or ability to control and curtail EV charging. So DER is kind of the catch-all for all the various resources on the distribution system that can be utilized, especially in the next generation of distribution operation. So hopefully that explained our meaning of DER. Moving on to the next one. Looks like we've got a few questions, as we typically do when it comes to cybersecurity. So Giovanni, if you want to touch on, there's a few questions just asking about how is cybersecurity dealt with in an IIoT platform.
Thank you, John. Well, thank you for the question. You're right, John. We normally get this question right away when we present. So normally customers are concerned about the cybersecurity when it comes especially to distributed control in the network. So to ensure the security of the information and the communication of the nodes, so the different IoT devices, we have implemented basically, we can say 4 measures. So the first one is a firewall, and this controls and blocks unauthorized access to the node. And it works especially well with the containers. So we have the containers running in the node. And as these run on an internal virtual network and on the Docker engine. And so the ports in the containers are basically use, so the container can only use the doors in the network unless they are told otherwise. That basically isolates them from external attack. We also have port knocking. So this is a service that allows us to open ports remotely with a specific combination of pings. And it's especially useful because it avoids port scanning from attackers. Then we have a TPM, that's a trusted platform module, basically a chip that oversees storing credential and encrypted information in the hardware itself. And lastly, the use of certificate and SSL connection. So that all connection to the node or from the node are encrypted and secure using proprietary certificates. Not only do we secure the information at the node, but also the communication between the node and the back office. So, for example, if we use our real-time information bus, then there is we use the DDS protocol, and we use which is implemented by a company called RTI, and they have a very, very fine definition of all the different levels of security. So encrypted the starting, encrypted through the communication, and then the back office normally have the security of each company. I hope that answered the questions.
Oh, fantastic! Thank you, Giovanni. The next one I can take. It asks, in the San Diego study, were the substations communicating directly to each other for automated switching, or were they reporting to the centralized control for automated switching? So I would say kind of neither. Basically, the approach we took was very similar to Georgia Power, where one server or one server that has the model of that entire cluster of automation, which included both substations and all the feeders and assets associated with it. One server modeled all that, and then that server would send all the automated switching commands, but then also be communicating with the centralized SCADA or DMS system so that there is that visualization. But that server associated for that cluster of automation would be actually sending and communicating those devices and communicating with those devices. So hopefully that answered that one. The next one, I think it's more specific to you, Giovanni. Have you been able to connect and control EV charging stations. Is there a protocol that you are using, or maybe a custom API or message sent to the EV charging station vendor equipment? Is that something that you can address, Giovanni?
We are in the process of integrating the EV. We had to wait for the EV chargers to be connected to the ring, and we are in the process doing. As I said, we have at this stage we have connected the building and the inverters, and we have connected the battery, and we are waiting for the EV, and the control part will be early next year available in the platform in Monash.
Okay, fantastic. And one thing I'll add, as part of when we're dealing with protocols and protocol management, part of this IIoT platform, it actually has a protocol translator layer that allows to interact with multiple different protocols. As we know, a lot of different protocols for a lot of different devices exist. So that's certainly something that needs to be handled by this platform. Okay, the next one, can you please expand on the template model that was used at Georgia Power versus the GIS-based model? So I'll go ahead and just field that one. So Georgia Power did not want to go through the process of GIS model cleanup and conversion, which if any utilities out there have gone through this, they know this is a pretty arduous task. So they wanted a simplified model specific to meet their distribution automation needs. So what we did is we created multiple templates with pre-populated devices, so switches and other devices along their feeders, and various line segments to allow them to build in a very time-efficient manner various clusters of automation. And from that, they created simplified models like one lines that are electrically accurate, but without any geospatial representation. And that worked perfectly for what they needed to handle the DA needs that they were looking for. So this streamlined the process greatly to allow them to scale to nearly 800 feeders now running on this distributed control scheme. So hopefully that explains what was meant by the templates that were used. Okay, here's another one. I'm not sure which one they're referencing. I'm guessing this is another one for Monash. For the voltage monitoring example, was it only modeled? Do you have actual monitored data showing the DER value for supporting the voltage? I'm not sure, Giovanni, does that make sense?
I don't know if it's referring to Monash. Probably it's referring to, anyway, in Monash, we are connected to the inverters. We're not exerting at the moment the control, so we can show the data from the inverters, and we can show the network data, and they're both captured and analyzed. I don't know if that answered the question.
Yeah, I wasn't real sure which one they were referring to with that one. So I believe that's all
about San Diego. If you use the renewable energy data.
So certainly, so certainly, maybe if that's what they're referring to, we certainly we used utilized all the existing devices out there. So the existing controls that are taking in, voltage, current, all that, all these advanced controls now that have that capability. All of all those data points are being fed back and used in that real-time load flow model. So if that's what they're referring to, then yes, we certainly utilized all the various data that was incoming from all the various intelligent controls modeled in the system.
Let me add, John, if we didn't answer one of the questions, they can send a detailed question, and we will try to answer it in more details.
Yep, absolutely. Okay, well, I think those are the questions that have come in for now. So I appreciate everybody joining, and Delana, if you want to wrap us up.
Yeah, you bet. I just want to thank everybody and thank the presenters for attending and joining us today. Please don't forget to take the short survey at the end of this. It's just 3 quick questions, and that's it. Have a great day, everyone.